Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics in the University of Helsinki. I hope I said postdoc and not PhD there, just in case. I'm a postdoctoral researcher. I started these streams when I was a PhD student and sometimes that still slips out. I'm a postdoctoral researcher at the University of Helsinki where I study cosmology. That means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically all of the cool things happening inside the universe. It's a great topic. I love talking about the universe. I love coming here on HAPS and chatting to everyone about all of the cool things happening inside the universe. Hey David, hey Med, hey Scott, great to see everyone. Thank you for joining as always. Wherever you're watching from, if you're on Twitch, if you're on Twitter, if you're on HAPS, if you're on YouTube, if you're on Reddit, welcome. It's great to have you all here. I'm an hour late. I am not an hour late. I know some of you have done the stupid thing of changing clocks that we do every 6 months. I hate daylight saving time. Just going to mention it again. Hate it. We haven't changed yet in Europe. We change in 2 weeks. So for 2 weeks, we're all going to be a bit out of sync. So simulating the early universe is the topic good for today, as David is mentioning here in the comments. And this is a topic that I'm not going to cover by myself. So I have a guest joining me today. I'm just going to bring him up on screen and then he can introduce himself. Let's see, you should be on screen now. Hi Dan, welcome to Cup of Cosmology.
Hello, nice to see you.
Great to have
virtually rather than in person.
yeah, we saw each other like 3 days ago anyway, but great to see you again. So, do you want to introduce yourself to everyone here?
Yeah, so my name's Daniel Cutting. I'm also a postdoctoral researcher, and my kind of most esteemed qualification is that I'm actually Deanna's office mate currently. So that's why we saw each other a few days ago. Deanna brought cookies into the office. So yeah,
it's a good way to win people over.
Yeah, a good way to win people over. Yeah. I work on early universe cosmology. I think you had another one of our colleagues, Anna, on recently, and we work on quite similar topics. So I work on phase transitions, and I'm interested in the first second of the universe.
The very, very early times.
Very
early
early times.
Universe. So I see someone's here saying simulating the early universe back when we were PhD candidate, even earlier than that, much earlier than that. We're going very, very far back in time. As James is asking, do we mean 1 billionth of a second? Not so far off. We are talking about less than a second into the universe.
Picoseconds, hundreds of picoseconds.
What is a picosecond?
I forget the number. What is it? 10 to the minus 50?
10 to the
or is it 18?
12. I would have said 10 to the minus 12. Well, let's just check that, but it's a very, very small fraction of the early universe.
10 to the minus 12, you're correct.
10 to the minus 12, that's good. I only know that because we said that with Anna when she was on the show 4 weeks ago. We have an important question from Scott here. How were the cookies?
They were very tasty, very tasty. Went very good with the coffee.
Yeah, they were good cookies. I should make more cookies. As Paul is saying, if you wish to bake a cookie from scratch, you must first invent the early universe. That quote from Carl Sagan, the real one, was actually in my master thesis. That was the opening quote of my master thesis. So great to see everyone joining here in the comments. Hello, welcome everybody. I see we still have not got the Reddit connection back. Reddit has been down all week from HAPS. It's a shame, but wherever you're watching from, it's great to have you here. So, as always, this is an interactive stream. You can all jump in with any questions, any point. Feel free to ask anything, and we will do our best to try to answer any questions you have. So maybe just to get started a bit, Dan, do you want to tell us what you've been working on lately, what you worked on during your PhD? Like, what exactly do you work on about this early universe? Hey, Lucia, great to see you in the comments.
Yeah, so I'm quite interested in this. The conditions in the early universe and how we can perhaps look for observational signals that might be able to tell us what things were like way back when. Because it turns out actually finding out what happened at these very, very early times when the universe was super hot and energetic and going through all these kind of quite exotic changes of state and in its infancy is quite challenging, and so it's difficult to it's still this kind of thing that we don't have the full picture of what was going on back then. And one kind of exciting thing that's happened kind of in the last decade is that we've had this first detection of gravitational waves, and these are quite an intriguing probe to these very early times, because gravitational waves, the cool thing about them is they propagate through space and change very little from when they were kind of initially released or generated. So if you can go and look at something that maybe let off a big burst of gravitational waves in the early universe, then maybe you can infer what was going on way back when. So I actually do simulations of certain phenomena in the early universe and look at the imprint that they may have left in gravitational waves, so that very smart people can go out and go and look for these things at upcoming detectors.
Awesome. So you've dropped a lot of important topics there, so we will come back to them. Just want to say thank you to Lucia for the Takeover Award. I do really appreciate the awards, and it's great to see you again here, Lucia. And everyone making comments, and hello to everyone. It's great to have you here in the comments, as always. Really, really nice to see you. So, you mentioned a lot of topics there. A lot of cool stuff that we are going to get into. But one thing that I want to highlight here is just how difficult it is to study the early universe. We're talking about something that was 13.82 billion years ago. That's 13 giga years ago. This is ridiculously long time ago. And one problem that we always have in cosmology is you can't really create a universe in your lab. You can't set up a new universe and watch what's happening. So in order to study the early universe, what we need to do is run simulations. We tell our computer, this is everything we know about the universe, now simulate it for me. Because that's our only real way of trying to figure out what was happening in the early universe. Of course, all of our simulations then need to be checked with observations and so on. But it is really an interesting question here of how we actually study this first picosecond of the early universe and how we actually get there. And I just want to go back to another thing you were talking about. You mentioned the recent detection of gravitational waves. Now, This was by the LIGO collaboration in 2016. Opened a whole new era to astronomy, is the catchphrase everyone likes throwing around.
The year I started my PhD. So quite an exciting time to start studying gravitational waves.
Yeah, definitely. It is also the year I started my PhD, but not on gravitational waves. But yeah, you definitely had good timing for that.
Yeah, for sure.
So just want to clarify here that detection that we had was of two black holes smashing together. We've also by now measured two neutron stars smashing together and potentially black holes and neutron stars smashing together. But these are not the same type of gravitational waves that you were talking about, right? Because the ones that you work on are not caused by black holes. So what type of things cause these early universe gravitational waves?
Yeah, so there's quite a few different phenomena, but the kind of one that I'm mostly interested in, or have spent most of my time researching, are phase transitions. So this is where the universe kind of changes state between two different kind of phases of matter, say. And kind of an example of this would be if you have, say, water that boils from liquid to gas, that's also a phase transition. And we're interested in when these phase transitions are called first order. So that basically is just a technical way of saying that you have the different states coexisting at the same time. So when water boils, it's a first order phase transition at kind of the normal pressure that you're kind of used to, which then means that you have bubbles of gas inside a bunch of liquid. So this can then lead to kind of interesting consequences if you have such a phase transition in the very early universe, such as gravitational waves.
Which is really cool if you think about this, because we're talking about something dramatic that happened at really, really, really early times that we hope we can see today based on gravitational waves, which is pretty cool. We have two good questions, and thank you, David Dunn, for the Love Burst Award. I really do appreciate all of the awards. So we have two questions here. The first one is from Paul, and I think it's a very nice question because we have the idea that in the very early universe we didn't yet have matter. We basically had energy. So if the early universe was basically made of energy, how did this create gravitational waves? You already mentioned this slightly, but I think Paul's question is mainly like, how do we go from this energy state to gravitational waves?
Well, I guess, yeah, so I guess that's like the equivalent of saying that you're kind of thermally dominated, right, rather than dominated by mass. And it's kind of actually, this is kind of intriguing because it also ties into the idea of mass, and kind of one of the interesting phase transitions in the earlier universe is Electroweak phase transition. Yeah, I won't get too technical there, but that's associated with the Higgs boson, which, for kind of particle physics aficionados in the chat, might be aware that that's the particle that's kind of attributed to giving mass to the other particles in the what we call the standard model. But yeah, to kind of loop back into the question of how you get gravitational waves from energy, I suppose you can generate gravitational waves whenever you have effectively like a large shift in energy or mass that breaks spherical symmetry effectively, and then because that creates a distortion in the gravitational field, or in slightly more technical terms, in space-time, that distortion then propagates outwards and releases the gravitational waves. So you don't necessarily need to have mass, rather than lots and lots of like thermally excited particles. Like you can get it just by having the propagation of energy, and you also have this energy mass kind of equivalence principle as well.
So the cool thing here is that all of these topics are very linked together, and we can jump from one cool topic to another. And you mentioned the Higgs symmetry breaking, and I wanted to bring up this cool image you can see on screen. Now, this image was made by Anna, the PhD student who joined the show some 2-3 weeks ago. I lose track of time, very recently. This is basically an illustration of what the Higgs field looks like. It's known as the Mexican hat style field. When you have a change in the Higgs field, you can kind of roll from one of these top of the ball thing to the bottom, and this is what generates properties of the Higgs field. Just wanted to show it because it's a rainbow figure, and I love rainbow figures, and I made this figure, so I wanted to show it on the screen. Now, you talked about electroweak symmetry breaking and said we're not going to get too technical, but I do want to come back to that because David also asked in the comments here, David Dunn, if something that could produce gravitational waves and a phase transition, for an example, is the freezing out of fundamental forces. And then you threw out the word electroweak symmetry breaking. So now I'm going to ask you to explain what is the electroweak symmetry breaking.
Yeah.
No, any topic you bring up, I might ask you to explain.
Okay. Yeah. So I should be careful. Going back to my like master's courses now, in trying to remember how much I can remember in detail. But basically, yeah, the electroweak symmetry breaking is when you have kind of these four fundamental forces that we kind of know about. You have the gravitational force, or gravity. You have the electromagnetic force. So that's electricity and magnets and radiation and light. And then you have the strong and weak nuclear forces, which are kind of slightly less, in less familiar to us in our kind of everyday walking about. They're very present, but they're talked about less, perhaps. But in the very early times, so when in this kind of first 100 picoseconds before that. The two of these fundamental forces were actually unified together. So the electromagnetic force and the weak nuclear force kind of combined to make the electroweak force. And electroweak symmetry breaking, which is kind of one of these potential phase transitions that we're interested in, is where these two fundamental forces split. And this happens via something called the Higgs Mechanism, and it relates to the Higgs boson. Yeah. Is that too technical? Is that
No, I think
too
it's
vague?
good. I think that's a good level. And as always, the people in the comments watching, if anything we say is not clear, do ask us, and we can re-explain it or find different ways of clarifying. So someone made a comment to me recently, which is honestly one of the worst things you can say to a science communicator, which is, everything they do is so brilliant, I don't understand a word of what they're saying. It's like, this is the worst thing. It's like, if you tell me you do not understand a word of what I'm saying, then we are failing at science communication.
Yeah.
So please, if you have questions, do ask. Don't sit there thinking that you don't understand. Please ask your questions, because that is exactly what we are here for. And if you don't understand, please tell me at a time when I can change it, not after the stream has ended. So, we've covered a lot of cool things here, and just bringing it all together again here, just in case anyone wasn't following there. The electroweak phase transition is where the two forces split, but in the standard model, in our standard picture, this would not produce gravitational waves. Can you give I'm going to ask you a tough question now. Yeah. Why would we not produce gravitational waves in the standard picture of electroweak phase transition?
Yeah, so it has to do with this thing that I said slightly earlier of the thing that I'm interested in when these phase transitions are first order, which is this kind of technical term for meaning that you have the two phases coexisting, but in different kind of parts of the universe. So if you imagine this picture of water, which you heat up and you boil the water, and you have like bubbles of gas appearing, which then expand and rise, and eventually you boil off all the water, and these bubbles of gas meet, and then you just have water vapor. So in the standard model of particle physics, which is what we use to refer to kind of all the particles that we have discovered, and all of the forces that we're aware of, and basically the things that we've actually directly tested and found. So in the standard model, with those particles, it just so turns out that in the early universe, this electroweak symmetry breaking doesn't happen as a first-order phase transition. So instead of happening as a first-order phase transition, instead you have something called a crossover, which is where the whole universe effectively transitions between the two states in a smooth manner. So instead of having this kind of discontinuity in these two different phases existing at the same time, so having gas existing alongside water in this analogous example, instead you just kind of have this strange thing where you would effectively have your liquid smoothly changing from being kind of more liquidy to more gas-like, without ever forming a bubble of gas. And this is something that can happen. It can also happen to water if you change the pressure. Then you can actually have a crossover between the liquid and gas transition in water as well. So it's kind of interesting that these kind of like really familiar things that we're used to thinking about in kind of our everyday also have these kind of direct analogies to what happens in these kind of complicated field theory models in the early universe.
I think that's a very nice explanation there. So
I guess I didn't get to the part of why that doesn't create many gravitational waves, though.
Sure.
Which is basically just that when you have these discontinuities, when those two different phases meet, and as these things expand, effectively these bubbles of the new phase expand. When these bubbles meet with each other, that's when you kind of get a production of gravitational waves. So if everything's smoothly changing, it's a much less kind of energetic or violent process, and therefore you don't have these kind of large amounts of energy shifting around, which then produce gravitational waves.
So I'm going to use that as a segue to our next topic, but before that, I just want to reiterate here that this means that within the standard model, we do not expect gravitational waves from an electroweak phase transition. This means that if we find a gravitational wave signal that matches some type of early universe phase transition, it would be a hint of new physics. It would be a hint of something that is not within our standard picture. And this is one of the reasons it's such an interesting topic, because not only does this give us a way of studying the first picosecond of the universe, it could show us where our models are wrong or where our models are not the complete picture. So it's a very, very interesting thing to consider, because we know that the standard model of particle physics is not complete. We know that things are missing. For an example, we don't know how to explain the fact that there is more matter than antimatter in the universe. And some models that try to explain this tie into producing gravitational waves in the early universe. So this is really a way of studying not just the early universe, but how the universe looks the way it does today. So you mentioned that... Sorry, you were about to say something.
I was just going to say, yeah, and that's actually one of the reasons that people first started looking at the electroweak phase transition and thinking, this should... possibly be first order, because one of the ways of explaining why there's more matter than antimatter is that the electroweak phase transition, if it's first order, provides a mechanism for that to happen. But if it's not first order, then you can't generate the matter-antimatter asymmetry from the electroweak symmetry breaking. So it's kind of interesting. Like it's like, well, if we can see the gravitational waves, then not only is that a signal that that there must be something else going on, because we shouldn't see them if you just have the standard model particles. So it's kind of, people sometimes refer to it as a smoking gun, but also you have this kind of direct link to other kind of interesting fundamental questions, like the one that you just mentioned.
Yeah, so it really is a cool way of opening up this whole way of looking at not just the early universe, but understanding how things came together, which is really cool. And before we go into what I wanted to talk about, there are two questions that we should answer here. So the first one by Paul is, do we map out these epochs of the first 100 picoseconds like the longer history of the universe? So it's quite funny, actually, when you go through your standard pictures of the history of the universe, the first 3 minutes occupy most of the story, because so much happened in the first 3 minutes that, there are books called The First 3 Minutes. There's an excellent book by Steven Weinberg called The First 3 Minutes, and it's like 300 pages of everything that happened in the first 3 minutes. And then afterwards, it's like, now we wait 100,000 years and nothing happens. Now we wait about 7 billion years, nothing happens. So really, those first 3 minutes, a lot is happening. So we do break it down. We don't get to the point of having like radiation domination, matter domination, like we do later on in the universe. But we do have things like a hypothetical grand unified theory, a hypothetical inflational period. And this does tie into a stream I did 2 weeks ago where we talked about all these hypotheticals in the early universe. It was great fun. There was a topic request by someone here in the comments, and it was a great topic to cover. And I just want to tackle James's question here, because we were talking about at some point how these early universe gravitational waves are different to the gravitational waves produced by a black hole. And James is asking the question of what characteristics differentiate these gravitational waves. So what's the main difference between the early universe gravitational waves and these late universe gravitational waves?
So I think James's question is actually what's the difference between two black holes compared to neutron star black hole.
Yes, and I misread that question. And yes, please go ahead and answer that.
So I think the answer there is probably you can infer the masses of the like you have these complicated to model these these black hole and neutron star, or black hole or neutron star mergers, you have kind of two main techniques. One is called post-Newtonian, what is it? Post-Newtonian dynamics or something like this, which is where you basically do these increasingly more complicated mathematical expansions to try and just really compute the orbits. And from those orbits, you can then go and compute what the gravitational wave signal would be. And so by varying the kind of the mass of the object, you can kind of shift and change what this gravitational wave signal. So I don't know if anyone here has ever gone and listened to this kind of audio analog of what the gravitational wave signal sounded like that LIGO went out and detected. But you can actually basically convert the signal into a sound and listen to what they call the chirp. So you can basically by looking in detail to the modification in this chirp, you can infer different properties of the two precursor objects. So the black holes or the neutron stars, and we know that there aren't black holes that have a mass below a certain. Oh no, actually, that's an interesting question. So that's not technically correct, but we know that there aren't any astrophysical black holes which have masses below a certain mass range. So we assume that those would be neutron stars. So you can look for the kind of the change in the gravitational wave signal in that. And here is an example of these signals. So by looking at the way that these oscillations are modulated, you can actually go away and infer what the masses and the spins and all sorts of other properties of the objects, both by doing this mathematical expansion of post-Newtonian dynamics or by doing numerical relativity simulations, where you basically put the Einstein's theory of relativity on a computer, and then you churn a lever and go, please tell me what happens when I put these things and spin them together.
So I didn't want to go too in detail about this, but now that we have it up, we have to. So the image you're seeing here on the screen. Sorry if I cut you off there. If you want to carry on, I can stop.
I was just going to say. The other thing to the looking at this kind of signal and inferring the masses and things is you can also go and look for when two black holes collide, you don't expect there to be any what people call the electromagnetic counterpart, which is basically radiation in the form of light. But when you have two neutron stars colliding, you expect there to actually be quite a big burst of electromagnetic radiation. And so that's how people went away and said, look, we've just had the first neutron star merger because we also saw a signal in gamma rays and other photons, and then a bunch of telescopes went out, and there was this mass effort by the kind of global astrophysical community to all point their telescopes at the sky and see if they could see any bright lights that had suddenly appeared where there weren't any before. So there's some really cool papers on that, actually. Really nice talks as well.
This is the problem with gravitational waves, that once we get started, we do not stop. We are very viable to go off on tangents about cool discoveries with gravitational waves. And I'm just going to take this chance to self-promote here, because you mentioned about Paul talks about gravitational waves. So actually, this Friday in 5 days, I'm giving a public outreach talk about gravitational waves.
Oh, nice.
It should be at same time that the stream started today, so figure out whatever time that was in your own time zone. Friday, I've just posted the link here in HAPS. I will tweet out the link as well. But yeah, stay tuned for that, because I'm going to be talking about gravitational waves for a whole hour, and I've never done a public lecture on this topic before, and I'm super hyped. So just want to go through this image, because now that it's on the screen, we have to explain it, as Georgia was saying here in the comments. And let me just say hi to Georgia. Thank you for being here. It's great to see you. And good luck on almost being done. Good luck on handing in your thesis. It's always a nice thing to be able to say. So yeah, what you can see here up on screen is a detection of the first ever signal of gravitational waves coming from two merging black holes. And as Dan was saying, what we can do is we can reconstruct what is happening. And the thing is, we've had 100 years to do this. We've been waiting to get a gravitational wave signal for a long time. So we've been able to create a catalogue of what we would expect for different things colliding together. So then when now we get two black holes colliding together, you can map it onto the existing catalogue to get the properties of the black hole, to get the properties of the neutron star. And this is one of the ways we have of telling them apart. And seeing as you mentioned it, we're going to have to put the video, because you mentioned we can turn this into an actual sound wave. So this is why it's often referred to that gravitational waves allow us to listen to the sounds of the universe. So I'm going to play two sounds. The first one is going to be the sound as in the actual frequency that it's measured, and then it's adjusted to fit the frequency that best adjusts to human hearing. And let me just find the video again. Now that Haps lets me share this video again, which is only came back very recently, but you mentioned this, so how could we not play it? I hope you can all hear the audio here.
Oh, cool. I don't think I've seen this version.
So what you can see here, I will play it again in a sec, but what you just heard here was the sounds of this first gravitational wave signal. The first deeper chirp that you hear is actually how it was recorded in the correct frequency, and the second higher pitched chirp is where it's been adjusted slightly just to match our human hearing. So I'm going to put it on again, because this is really cool, and I wasn't planning on doing this. I didn't even have it uploaded, but because you mentioned it, how can I not bring it up? So let's just do it one more time here. I will never get bored of listening to that, so thank you for giving me the excuse to bring that up on screen.
What does it actually mean, like the frequency that it was recorded? I guess. sorry, that's really mean. It's a mean question, but like, because it's basically like the oscillate, like the way that it actually works is the cancellation of photons that have been beamed along the. This is how these two experiments measure, right? You have photons that go along these really long tubes, effectively super cooled tubes. They bounce off mirrors, they get reflected back loads and loads and loads, and then they come back and interfere with each other, and they're set up so they interfere deconstructively if there isn't a gravitational wave passing through. So if they interfere deconstructively, a gravitational wave passes through, it distorts the space-time, and then you measure a signal in the photon detectors, because you have because now they're no longer interfering deconstructively, they're interfering constructively and deconstructively, and then that is then mapped into, I guess, frequency space.
Yeah, so the
so is it that? It's the signal in the photons that is modulating in frequency space, and then we pretend that it's a sound wave rather than a light wave. Is that?
Yeah, I mean, I was a bit careless saying. I was careless saying it's in the frequency in which we measure it. It's good that you called me out on that. So
no, I wasn't calling you out. I was actually just thinking to myself, because I always think when we listen, we say that we listen to it, but we're still actually seeing it through a detector that is actually measuring light. So it's funny.
But we measure the light, but then we can reconstruct this waveform here, and this waveform has a specific frequency. I mean, here we're showing it as time progresses from left to right. So you can convert this into a frequency. Right, so you have the frequency of the wave that is actually corresponding to the waveform of the two black holes smashing together.
Right, and this is the strain. Okay.
This is the strain, which can be converted directly to a frequency. So it's the same thing, just strain is a more technical term for it. This frequency is actually in the audible range. So the first clip that you hear, the deeper one, is directly converting this waveform that you see here to sound. And the second one is just shifting it to pitches that we're more used to hearing. But yeah, we don't directly measure the sound. What we measure, as you were saying, are the photons that are moving in our detector, and that shows us the gravitational waveform which we convert into, from which we can get the strain. So it's a convoluted way of going around it, and it's not completely correct to say this is the frequency that was measured, but this is the frequency of the reconstructed waveform that was measured.
Yeah, there we go.
Yeah. Don't worry, James, there are no basic questions. What type of wave are they? Are they electromagnetic waves? They are waves of space-time itself. So they are ripples in the fabric of space-time, which is kind of cool because we say everything moves through space-time except space-time itself. So this really is space-time itself moving, which is very, very cool.
Also very hard to visualize.
Very, very hard to visualize. We do have a comment here from Paul of, I assume it's not just a wave, it's lots of waves as the black holes orbit each other spiraling in. Yes, it's not just one gravitational wave that hits you. You get the whole sequence here. In fact, if you look at what you can see here, at the beginning there's kind of a flat waveform. Looking at the middle panel here, at the beginning it's kind of flat. Then it speeds up, and then eventually it stops. So this is as the black holes get closer and closer, they accelerate, they start merging faster and faster. So we have two black holes spinning around, gradually falling into each other. It gets faster, then they eventually crash, they finish the in-spiral phase, they have this big burst of gravitational waves, and then it gradually dies out. So you don't just get like one wave, you get this whole shape. Hope that answers that question. And we went way off tangent here. We were supposed to be talking about simulating the early universe. But this is the thing, when gravitational waves come up, how can we not talk about it? And once you mentioned listening to the sounds of the universe, I had to play the chirp because I have it ready, just for times like this. So I wanted to segue into another topic just now. I've lost a nice connection at this point, but we were talking about earlier on about how these bubbles that you have in the early universe coming from the phase transition, if they're smooth, they won't produce gravitational waves. If they're not so smooth, if you actually have these bubbles, you will produce gravitational waves. So then we can actually tie it into what you specifically work on. And I'm going to share a simulation that you shared with me, where I believe it's one of the nicer ones. You sent me lots. I'm just going to share one.
Yeah.
And then
I'm curious which one you pick out.
Not the 1.5 minute ones. I went for the shorter ones. So I think this is the one that I wanted to show first. So first we can see the simulation, and then you can explain what is happening in the simulation, what we're seeing, and how this is related to what we were talking about.
Yeah.
And when it finishes,
so far it's just very, very pretty.
Yes. And I appreciate that you use Viridis because it's my favourite colour map, and it's the one I try to use all the time. So I do appreciate that you use this one. It's the best one to use.
Perceptually uniform.
Yes, and it's just so pretty.
Yeah, so maybe...
Okay, I'm going to play it again, and you can tell us what it is.
So maybe just... Yeah, okay. So this is basically... In my simulations, what I effectively do is I have like a box, which I define on my computer, and then I've got a bunch of grids of points in this box, which is the points that I'm kind of simulating the phase transition on. So you kind of imagine that I've just gotten a subsection of the early universe, like a cube out of it, and I've started to put bubbles of the new phase in this box, and then these bubbles want to expand and like take up the space in the... Yeah, they want to expand because this new phase is energetically favourable, which means that it wants to kind of sweep out the old phase. And the other thing to know about these simulations is that Is this a lava lamp? Tell us the truth. You're right. You've caught me out. You've caught me out. It is just a lava lamp.
Definitely just a lava lamp.
Just a lava lamp. Okay, I'll stop my explanation now.
Just a pretty lava lamp that we found.
Yeah. Yeah, you've ruined my research career. No. The other thing to know about this box is that it's periodic. So what that means is that anything that comes in through one side of the box or goes out through one side of the box comes in from the other edge. So you can kind of think of this as you can kind of think of this as being like this little patch. I'm pretending that this little box, this little patch of the universe is representative of the rest of the universe. This is a relatively small simulation, so that's not very true, but it's good enough for our purposes. So what's happening at the beginning is there's one bubble that's placed on the kind of corners of the points of the box, so you can see that expanding. And you can also, I should also say that this is a slice out of the 3D box, because it's very hard to make 3D movies, so we make a 2D movie with a slice through the box. The colour that is shown here corresponds to the velocity in the fluid that's kind of present in the early universe. So early universe, very, very hot, dense plasma of particles. As you mentioned, it's kind of energy dominated, so they're highly relativistic particles. They make up a fluid, and when you nucleate these bubbles of the new phase, which you can see expanding, they actually push this plasma around kind of give it some velocity. So that's what I'm kind of showing. And these bubbles, as they expand and collide with each other, once they've all collided, the fluid still remains perturbed and is moving around, and you can actually see what you can effectively see here are sound waves that are propagating through this fluid. And the cool thing is that these sound waves turn out to be like a really efficient source of gravitational waves, which is one of the reasons why we think that you might actually be able to go away and listen for these gravitational waves produced by these sound waves in the early universe.
So it's really cool. I just kept looping the simulation because unfortunately I can't go back with apps. I just have to unpresent, represent. But it's cool that I can present now. So we have a few questions here because you gave a very nice explanation here, but I think we might have lost a few people. So I want to go back to a few things that you said.
Sure.
So first of all, there's this thing about the sides. What goes out one side comes back inside the other one. And David Howden is asking, does this mean we're assuming like a donut-shaped universe?
No, it's not. It's not that. Like, it's not saying that whatever comes out one side of the universe comes back in through the other. It's more just that I can't simulate an infinite universe. Like, there's not enough size on my computer to do that. So I have to make a approximation somewhere. So you have to decide what happens at the edges of your simulation box. One choice would be whatever hits the edge of your simulation box effectively gets absorbed. So that's one type of condition for the boundary. But that's not really very representative of the early universe. There's not just some patch where stuff's going on and some small patch where stuff's going on, and then outside of that patch nothing's happening. So instead what you say is, okay, this bit of the universe that I'm simulating isn't any different to the bit that's beside it. So let's just pretend that I can just stack an infinite amount of these cubes and say the exact same thing's happening in each one. And if you do a big enough simulation, this only had 8 bubbles total in it, but say you have, 6,000 bubbles or something, then you start to get to this point where you can kind of fairly accurately say, well, they're all placed in a random enough position that it's kind of statistically representative of the stuff that's going on around it. So here you probably expect from this simulation to have some inaccuracies that come from lack of statistical representation of reality, but as you go to bigger and bigger ones, then you kind of get away from that.
Yeah, it's a problem that this does require a lot of computing time. So just to recap here, Dan made this grid of the universe, this nice little box, You pretend that this box is a fair sampling of everything going on inside the universe. Ideally, if we had infinite computing time, you'd do a very big simulation. We don't, so we have to scale down our simulations. But then a way to be more realistic is that we assume that what's happening here can be mapped onto the next box and so on. So a bubble that goes out one side is equivalent to a bubble coming in from the other side, because we assume that all boxes have a similar amount of bubbles. Now, we jumped into this after we went off on a tangent of gravitational waves, so just bringing it back, especially because a few people might have joined late. What are these bubbles of? What do these bubbles represent?
Yeah, it's kind of complicated. So the bubbles represent different states of matter. And the kind of thing that we try and do in our group is we try and be fairly agnostic about exactly what kind of phase transition we're studying, because there can be various different ones. But generally, the distinction is something is a bit different inside one of these bubbles to for the particles that make up the universe compared to the particles that are outside of the bubble. So, for example, if it was the Electroweak symmetry breaking, the difference is that inside the bubbles, the Electroweak symmetry is broken. Outside of the bubbles, the Electroweak symmetry is preserved. So that kind of, and to go a bit more technical, that means that the Higgs field has taken a vacuum expectation value, but I don't know if that will mean anything to anyone in the chat.
Well, actually, if anyone was watching the stream 2 weeks ago where Katie Mack joined, we talked about possible ways the universe could end. One scenario we talked about is the expanding vacuum ball of death, which is basically
the same thing as this.
It's the same thing as this.
Exactly the same thing. I read the same. The kind of introductory papers for this topic in my PhD was these vacuum decay papers, when people are interested in the kind of what happens in the very late universe. Exact same mechanism. Actually, in the same field, the Higgs field, quite often. So, yeah.
Yeah, so you could imagine that each of these bubbles is an expanding bubble of death that is going to wipe out the universe. Now, that's not exactly what we were simulating, but the physics is pretty similar. Now, the difference here is we're hoping to see some leftover signal. You can still see here on the simulation, after these bubbles have collided, as Dan was saying, you have these sound waves, which can produce gravitational waves, which we hope to detect to be able to understand everything that was happening. Of course, if these were bubbles of death, we won't be able to measure anything because we wouldn't be here by the time this reaches us.
Yeah, fortunately, this happened before we were hanging around. Otherwise, yeah, this would. I think if you were hanging out in one of these simulations, it wouldn't be very pleasant.
Yeah, it wouldn't be a good place to be. So, Georgia, I think Dan answered the question, but just as an example again, a type of phase transition is when you go from solid to liquid water. When we're talking about phase transitions in the early universe, one example is when the forces broke apart. Depending on how these different forces broke apart, you would have different properties in the universe, and these bubbles represent the different bubbles of the new physics taking over the old physics. You use a word that is always confusing and that I still need a reminder of what it is sometimes. So you said these bubbles nucleate. What does that mean?
Right, yeah.
I'm hitting you with the tough terminology.
I forget that's even jargon. So, yeah, nucleate basically just means kind of appear, I suppose. Like form. Bubbles form. I guess nucleation is something that happens like when you boil water, or also if you take, I don't know if you've ever gone and seen these videos of where someone takes like a bottle of water, and you have if you have really pure water and like a quite smooth bottle, then you can put it in the freezer, and what you'll find is when you take it out, sometimes the water has gotten to beneath the temperature for which it would freeze, but this hasn't actually happened yet. and you can kind of tap the water bottle against something, which and that motion creates a nucleation seed, out of which the water will start freezing, and you can actually see this kind of happening in real time.
Which is really cool.
Yeah, so nucleation basically just means the appearance of the kind of new phase.
Yeah, I find that word unnecessarily complicated in general, because we all throw it around like bubble nucleation, and anytime I try to think of it, it's like I'm sure there are hundreds of synonyms to nucleation. Of course, we use nucleation because it determines the context in which we're using the word. And thank you, David, for the love burst award. I do appreciate all of your words. Just keeping on the topic of nucleation, because I found an example that really helped me understand what we mean about nucleation. And that's, I'm going to get rid of your simulation now. We can bring it up again if we need it. So one thing that you've probably all seen is a cool experiment of putting Mentos in Coca-Cola, shaking it, and watching your volcano happen. So when you put the Mentos inside the Coca-Cola, the Mentos basically serve as a place where bubbles can nucleate. So all of the bubbles that start forming this volcano actually start around the Mentos. And here you could say this is where the bubbles nucleate on the Mentos, and then they spread outwards. And it was when I read that example that I actually understood what we mean by nucleate. So I'm sharing that example in case it helps someone else. Now, going back to your simulations, because that is something we wanted to focus on a bit more. The simulation that I showed was a 30-second long version. You also sent me a 1.5-minute long version, which I think is the same, just slowed down. And David here is asking, how long did it take you to produce that movie?
Well, like, it took me several hours tapping away at my keyboard, trying different visualization options in Python. Hours is probably an underestimate, probably days. But
how
in
long
terms
did
of
it
actually,
take to run?
yeah, I guess that was the answer that you were searching for. So in terms of actual like computing time, I think these simulations, because they're not so big, because we were trying to do like a scan across a parameter space, so we were doing lots of these simulations. I think they took around 10,000 hours, 10,000 CPU hours. So that would be a really long time to wait if I actually had to like sit down and wait for that to finish. So I didn't have 10,000 hours in my PhD to wait for these to run. So what you typically do is you put, instead of running on just one computer or one CPU, computer processing unit, you instead split the problem up into lots of tiny like sub-problems and get a different computer to run each one. So we have these big supercomputing clusters, and by splitting the problem up, you can leverage the power of industry and the ability to produce lots of computer chips, and make all of these jobs run in parallel. But then there's kind of interesting problems there, because how do you split up the problem? For us, it kind of makes sense to split the problem in space. So we have this 3D box, and so you split up and say, okay, well, this computer's going to handle this bit of the box, and this computer's going to handle another bit of the box. But then you have to tell those computers how they're going to talk to each other to work out what happens when at those boundaries between those sites in the computer. So they have to send information back to each other, and you have to work out how to efficiently do that. And that's how I spent a lot of my PhD.
David Dunn is pointing out that using a lava lamp would have been quicker.
It would have been a lot quicker. I'm not sure I would have got published, but it would have been quicker.
Also, you said you didn't have 10,000 hours in your PhD. 10,000 hours is 1.5 years, so feasibly you could actually write that long.
Damn.
But you don't.
I'm not so good at converting. Yeah.
Oh, I googled it. I did not do that
Okay.
conversion in my mind. I asked people to do
I'm
it
rubbish
for
at
me.
mental maths.
I can manage some mental math, but the conversion to hours always annoys me because it's like a 36, or
Yeah.
it just makes everything harder. Like, give me 50s, I can do. 36, I can't do. So we had a couple of questions here, and I know one is just trying to get me to show the CMB image, which I no longer have to do because it's in my logo, so we do see it at the start of every stream anyway. But we were talking about these bubbles nucleating. We use the example of Mintors and about the frozen water. So David Howden was asking, does this mean that in the universe there needs to be some type of irregularity around which the bubbles can nucleate, or around which the bubbles can form?
No, because I mean there could be. There's like lots of interesting papers on using primordial black holes as nucleation seeds for phase transitions, which is super cool. Which is also a pun because you have to supercool the fluid to create. Anyway, never mind. But you don't need irregularities in the early universe because there are kind of two different mechanisms for these bubbles to form. One is quantum tunneling, so you can have some region of the universe quantum tunnel into the new phase. So one kind of aspect of the thing that prevents these phase transitions occurring, the thing that prevents the whole universe just suddenly switching from one phase to another phase, like in a crossover, so just kind of smoothly continuing from one phase to another phase, is you actually have to have some barrier in potential energy that separates the two different phases. So you can have a bubble nucleate via quantum tunneling where some bit of the universe just decides to tunnel through this barrier and appear in the new phase. So that's one thing. And then another way of it happening is just via a thermal fluctuation. So you can have some bit of the universe just gets a bit hotter or a bit more energetic, and that allows it to have enough energy to move over this barrier into the next phase. Because the barrier is basically there's not enough energy to traverse the barrier into the new phase. You have to put some amount of energy in to transition, which is kind of like with water. You know, if you have water and you boil it, then you have to keep the heat on for the bubbles to keep forming. So you're kind of injecting energy, and the water's not getting hotter. It's actually it reaches boiling point, stays at that temperature as you keep injecting energy, which gives it the energy to traverse the barrier and turn into gas in certain regions.
Nice.
I think I got too excited there and maybe said that too fast.
No, it's fine. As always, if there are questions, keep them coming. We are approaching 1 hour, but there are still 4 open questions that I want to address just from here in the comments. I think we could just spend hours talking about these topics, but there are 4 questions. So I will go back to one earlier. Now there's 5 questions because they keep appearing, but do keep them coming, please. We do appreciate the questions. So when you were talking about the way you split this up in space and you have different computers running different parts, Paul says it seems simpler to let each computer run a different set of parameters if you were doing a scan instead of lots of computers cooperating on each iteration. Would you agree with that?
We do that sometimes, but again, 10,000 hours is 1.14 years. I didn't have that time to wait in between, because sometimes there'd be a bug, and if you run and it takes 1.14 years, then I'd only be allowed like 3 bugs in my whole PhD, which is like just way less bugs than I had. So. But we do sometimes do that. You know, there's some when things are weighted in a different way. So where maybe instead of taking 10,000 hours, it takes 2 hours or something like that, and I want to run 100 or 200 points or 300 points. Then it makes more sense to do those in serial. So you just say, I'm going to get 200 computers. They're all just going to go off and do their own individual problem. so I do that sometimes, but you just choose a different strategy based on the kind of the size of your problem and the number of times that you have to do it.
Nice. So I want to go back to a question that Paul asked quite a while ago when we were playing your cold video with the bubbles. See, that's a really nice thing about this topic is you get cool simulations. You know, what I worked on in my PhD is like, here's a static plot, and then I have to explain it, and you get videos. And honestly, it's so much
Yeah,
fun.
honestly, it made my talk so much easier because
like,
even if I wasn't like understandable at all and didn't get any of my points across, people came out being like, oh, that was a nice talk, because there were some nice videos.
Yeah, you've got cool videos that just makes everything so much easier to explain.
Yeah.
So when we were showing your cool video with the bubbles, Paul asked, is each new bubble the same, or does it have random initial conditions? And this ties into what you were saying about the thermal fluctuations.
Yeah. So
It's a great question, by the way.
yeah, it is. I guess in reality we don't, like the nucleation of these bubbles is actually quite a complicated thing. We don't have like a super clear picture of exactly how that happens.
Working on that.
Yeah. You also.
No,
I thought you meant.
we
yeah. I was like, oh,
scientists in
tell me what you've been doing,
No,
Diana.
no,
I
no.
wasn't aware of this project.
No. I was like, we physicists in general are working on these things. Please don't throw that at me.
Yeah. I've got someone who I could get you to speak to regarding that. So in principle, these bubbles could vary, but what we do is we put in what's called the critical bubble, which in some ways is thought of to be the you can kind of do these techniques to work out the profile of a bubble that is the most likely bubble to form probabilistically, and we use that as the initial condition. And so in my simulations, I've put in that all of the bubbles are the same, they're just in different positions. And then the bubbles vary depending on different runs where you're kind of simulating slightly different theories. And then the results are different. But for each individual simulation, all of the bubbles look the same.
Nice. So there were two questions that I'm actually going to tie together here. And I think it's going to be a nice way to wrap things up. So before I go to that, is there anything else you want to tell us about the cool movie we were just playing and about the time investment? Because, it's a 30-second film, but the amount of time and energy and effort that went into that is a lot. So is there anything else you want to tell us about the simulation before I move on to two other questions that we had here? I can play it again if you need inspiration.
No, nothing that springs to mind. I mean, there's a lot of cool stuff going on in those videos, and I could talk about them for hours. In particular, how all the different ones that I sent you are different to each other and what we learned from each of them. I think the nice thing about the videos is that with these simulations, it's quite hard to kind of appreciate what's going on. And often, actually, there's not... What the videos are useful for is kind of understanding enough of what's happening to then go away and to form this like qualitative picture, and then you go away and then you go, okay, so this I could see happening in the video, so how do we go and check what like impact that has quantitatively? So like how do we make some plots of some like varying quantity that tells us a story in a more kind of scientific way than saying, hey, we saw this cool thing happening in this video and we think it means this. How do we actually go in a way and test out what actually happened in a simulation?
Nice. I was just looking for another, because I actually uploaded two of your simulations and I see that one of them has disappeared from my list of uploaded stuff. I don't know why, but we had one and I think it would take us quite a while to go through another one as well.
Yeah.
But yeah, I mean, these simulations are really cool. They're great for talks. They look amazing. But I think it's important, the takeaway here is you're saying that the simulations are not everything, or the movies at least are not everything, but we can use that to really gain a deeper understanding. Because obviously we show here like these cool bubbles colliding, but there's a lot of physics behind it. So I don't in any way want to downplay the thing if you just make cool videos. It's like they're cool videos that tell us about the early universe. and it's pretty impressive. And I love all of the videos that come out of the group. They're so cool. So many fun things to show.
Yeah, the videos are my favourite part, but there is some science getting done as well, so that's nice at least.
Yeah, and it goes hand in hand. Like, you make the videos, you learn stuff, and you learn stuff to make more videos. It's really cool.
Exactly.
Just means you have an easy way to explain it. That's not let me just bring up a figure and go through everything happening inside my boring static figure.
Yeah. I'm pretty grateful of the ability to show cool movies.
And it does make it such an appealing topic. It's like, hey, we have cool movies. It's like, join us. We have the cool movies. Yeah. Who doesn't want to
almost as effective as cookies for convincing people to join your research group.
Yeah, now we can advertise it like our group does cool movies, and we have cookies. There's no reason to not join us, and it's in Finland, which is the best country in the world. So
I've just seen Clevin just said, are the temps of the simulated environment reproducible by the LHC today? And the answer is no. It's too hot.
Too hot. We're talking about early picoseconds. This is really, really long time ago. We have a question from Knowledge on Twitter. I'm glad the connection to Twitter is working. That's good to know. What are the necessary tools one has to know in order to work on cosmological simulations? And let's keep the answer short because we are over time.
To work on cosmological simulations, I guess you need to have done some physics courses. Ideally a cosmology course, and then particle physics can come in handy as well. And then
coding.
Coding. Yeah, if you can pick up some Python is quite widely used, particularly in prototyping. But then often if you want to run actual big simulations that have to be fast and efficient, then quite often C or C++ or heaven forbid Fortran, if you're working with a very old school code, or there's some new programming languages coming up like Julia and stuff like that. But yeah,
I've heard so many good things about Julia.
Yeah,
everyone tells it as the best thing.
Yeah, I'm quite excited to try it one day, but I've not got to dabble my toes in there yet.
Yeah, that seems like the type of thing
coding
that I would
and
like
physics.
to know. Yeah, coding, physics, both of those. A bit of maths just to understand, what's going on. Math, coding, physics.
And some social skills, so you can go and pester your supervisor to ask what's going on.
To help find the bugs that you can't wait
exactly.
10,000 hours to find.
Yeah, perseverance.
Perseverance, I think that's a requirement for all branches of physics, and just a smidge of craziness to actually take on physics in the first place.
Nice one to David Dunn, who apparently did their coding in Fortran.
And David Dunn is an astronomy professor. He's a PhD in physics as well.
Okay,
PhD in astronomy, sorry. And yeah, coding in Fortran. I have done coding in Fortran and I did not enjoy it. Actually, during my bachelor thesis, my supervisor gave me a code in Fortran and I just rewrote it in C. And that's how I taught myself C, because I refused to work with his Fortran code. And it was good because I learned how to use C.
I used to complain about the variable names in this code being so incomprehensible, and then someone told me it was because you had a character limit in Fortran, so you just can't have they have to be called really short abbreviations. It's like, what is LHEX 2PY? That doesn't make any sense.
Yeah. So, but it's cool. It's really cool. But yeah, you need some coding. Fortran is not cool, but it's cool to know that you get to tell the computer to simulate the universe. It's always a nice feeling. And when your simulations work, and you might be the first one to ever see a physics problem visualized thanks to a code you've run, that is an incredible feeling. And for me, that makes up for all of the bugs and for all of the days you're bashing your head against the wall, because you actually get to simulate something and go, hey, look what I just made. It's a pretty cool feeling.
Yeah, for sure.
So we had two questions that I wanted to address. One was by Paul some time ago, with definitely an ulterior motive, of would different theories of what happened in the very early universe have artifacts you could test for in the CMB? And then we had another question from James of a serious but not serious question. Are the scientists studying different post-Big Bang timeframes, and are there sweet spots to study? And I'm going to group both of these together. And first of all say that the universe, the history of the universe is one continuous journey. Everything that we're talking about in the early universe has impact on everything else that's happening later on. So you do kind of move from one place to the other, but some people specialize in a specific time frame. And I wouldn't say there's a preferred time frame, but everyone has their preference. Like, my favorite time to study is the CMB, just because why wouldn't it be? But the first picosecond you saw today is amazing. The people studying the gravitational waves coming into LIGO is amazing. And I want to take this chance to show an image, because we've talked about gravitational waves of a couple different types. And I want to bring up the full spectrum of gravitational waves here. So when we talk about light waves, we're accustomed to thinking like there's different energies for light waves. You can have high energy light waves, you can have low energy ones, you can have everything from gamma rays to microwave. We can do the same for gravitational waves. There's a full spectrum of gravitational waves depending on the frequency or on the strain, which goes back to what we were saying before about how we listen to them. And depending on what's producing the gravitational waves, it's going to have a different frequency. So you can have like very, very early universe quantum fluctuations produced by the Big Bang itself. These would be on one end. And then you can have things like the phase transitions that we're talking about. You can have supermassive black holes smashing together. You can have normal black holes smashing together. And you cover all of these different ranges. And I'm not sure how well you can see the image, how well it's showing up on your screens, but what you can see here is on the left we have the higher energy gravitational waves, and on the right the lower energy gravitational waves. Is that correct? Or is it flipped? It's flipped, right?
Smaller, what is it? Smaller frequency on the left-hand side. So
yes.
Yeah, I guess, yeah. Higher energy, smaller frequency.
Yes, thank you. Thank you for confirming that with me. This is the time when we're both like, anyway, lower frequency on the left, higher frequency on the right. And yeah, I should have prepared this plot before bringing it up on screen. But the idea is, depending on how you produce these gravitational waves, you're going to have a different frequency, and that means there are different ways of detecting them. So everything we talked about LIGO and Virgo, these are ground-based detectors. These are what's focusing on gravitational waves coming from black holes smashing together. These are the biggest gravitational waves that we could hope to see. Then slightly smaller ones, you can have the ones produced by supermassive black holes smashing together, or the ones produced by these phase transitions. And to study these, we need a space-based detector, and this is where LISA comes in. So LISA is a mission that's set to launch within the next 15 years, and it's going to try to measure all of the stuff we talked about today, which is pretty cool. And because no stream can be complete without the CMB, and tying into Paul's question, if inflation itself, or the very, very early period of the universe, produced gravitational waves, these could leave an imprint in the CMB. So if we ever find a gravitational wave signal in the way the photons vibrate, the direction along which the photons vibrate within the CMB, this would be a hint of gravitational waves coming from inflation. So the CMB itself is also a gravitational wave detector, because of course it is. The CMB is everything. And so currently we have not found any gravitational waves within the CMB, which means we can put a lot of limits on what inflation might have done, because we haven't seen gravitational waves in the CMB just yet. So there's a lot of different ways we can measure gravitational waves depending on how they're produced. Do you want to add anything about this figure, Dan? Because there's a lot to unpack in this figure.
Yeah, there's so much in it. Pulsar timing, super cool. That's like measuring you have like, so pulsars are basically, I think are they active galactic nuclei? Is that right?
Basically, why would you go down pulsars and ask me this? Yes, I'm going with yes.
Yeah, supermassive black holes in the early universe that are kind of spinning and sending out lots of gamma rays, which reach us, and we see them in photons, and you can basically measure from these photons. You can basically use this collection of pulsars around the universe and the delay of these photons arriving to us. You can track whether there's gravitational waves propagating through the universe between these supermassive black holes at quite early times. It's super crazy. And people actually do that, and that's their whole job. It's
really
mad.
Cool. So just pulsars are rapidly rotating neutron stars, right? The ones that are.
Am I thinking of quasars?
Quasars. Yes.
Am I thinking of quasars?
Yeah. So pulsars should be a rapidly rotating neutron star, but they basically behave like a lighthouse, so they emit a certain amount of light that we know the frequency. And we can use this to measure gravitational waves as well, which is kind of cool.
Yeah, super cool.
But yeah, there's a lot to unpack. Didn't mean to cut you off there. I was just thinking like pulsars, because I remember a talk at some point where I had to say rapidly rotating neutron stars, and every time I did, I got a laughing fit for some reason. And in the end, I just skipped that sentence from my talk because I couldn't do it. So yeah, pulsars are rapidly rotating neutron stars. Now I can do it. But yeah, I think this figure is cool, and we could probably spend a whole hour talking about everything inside this figure, but I'm just flashing it at the end. And I'm using this as, again, an opportunity to advertise the outreach talk I'm giving on gravitational waves on Friday, because this figure is one of the few that I've already added into my slides. So this one's going to be there. Okay, so we are 15 minutes over time today because we got carried away talking about a lot of cool topics. So, right, yes, we mess up with the frequency there in the figure. We should have looked at the figure properly, but in any case, you have low frequency, high frequency, depending where they're coming. I like to think of it as like the biggest ones we can see were the ones on the right, and the smallest ones were the ones on the left. Then it's easy, and then we don't need to think about frequency and energy and get confused when we don't know how to convert between the two. Okay, so we are 15 minutes over time. This has been super fun. Dan, is there anything else you want to talk about or tell us about? Because we can keep going if you want to. So is there anything else maybe to wrap up?
Here.
Yeah, anything else you want to mention or talk about before we wrap up? Any piece of work you're super proud of that you just have to advertise?
I'm proud of all of my work equally. No.
That's cool. And we already showed your simulations, which is really cool.
Yeah. I think those visualizations are some of my proudest. I think they came out really nicely, and yeah, there's some interesting stuff in there. Yeah, I don't have very much generally accessible stuff. I could pitch my papers, but I think they might be not aimed at quite the right audience.
If you want to know more, check out the papers. That's always the way. If you want to take it to the next level, read the papers. Okay, so this has been super fun. Thank you everyone for all of the cool questions. We had some really cool questions today. As always, you people always ask great questions. So thank you for all the cool questions, and huge thanks to you, Dan, for joining me. It's been great to have you on the show.
I've just realised I can pitch our Vimeo channel.
Oh, absolutely, yes. Somehow I have not advertised that yet. Yes, let's advertise it.
I completely forgot. Let's find it.
If you have
here we go. I'm just going to put it in the chat.
So for anybody not watching on
HAPS,
for anybody not watching on HAPS, there is a Vimeo channel. How can someone find it if they don't have the direct link? Isn't it just Cosmic Strings on Vimeo?
It's Cosmic Defects on
Vimeo.
Yeah.
Do you want to just tell us what goes on this Vimeo channel?
I think it's mostly just a place that we decided to plonk all the videos that we make from our as part of our research, not just for public outreach, but also because it's useful for when we write a paper. Quite often, some of because we use the videos to kind of inform our understanding of what's going on. It's quite easy. It's useful to explain things to other researchers to be able to just say, go and look at the videos at this link. So that's where we put our videos, often with a bit of explanatory text of what's happening. It's a collection of different researchers, so it's me, Mark Hydemarsh, who's at Helsinki as well, and Sussex, Yanni Dahl, who's a PhD student at Helsinki, Anna, who's already been on, has made some, including when she was a master's student, and then some of the earlier videos I think are made by David Weir and Neil Bevis and David DeVirio. I think that's everyone. Hopefully that I've given credit to.
There's a list on the Vimeo channel as well of everyone.
Oh, there we go. I didn't need to do that then.
It's good to advertise everybody's work.
Yeah, the actual simulations are 3D. Except for the ones on the Vimeo channel, which are 2D and specify that they're 2D.
Yeah, but as Dan was saying before, showing the full 3D one is sometimes hard, so we take slices through them. But on the Vimeo link, there are also some of the full 3D boxes, which are really, really cool to watch as well. So do check that out if you want more.
It works quite well for cosmic strings, because you can see the strings moving through 3D space. Doesn't work so well for bubbles, because they all get on top of each other. And
gets a bit messy.
Yeah.
But yeah, thanks for advertising that channel. It's a good thing to advertise. So once again, big thanks to you for joining. It's been great to have you. And as always, you're welcome back on the show anytime. If you ever want to come back again, you're always welcome back. Big thanks to everybody joining in the comments. It's been great to have you here. I'll be on a line again next Sunday, same time as always. We don't yet change clock, so that's 7 p.m. Central European time. Figure that out in your own time zones. As always, cosmology.com has a time zone converter, so you can always figure out when I'll next be on in your own time zone. But Sunday, next week, I should be on again. Don't yet have a topic prepared for next week, so we'll just wing it, or I'll think of something during the week. And then the week after, I'll have another guest on. So do stay tuned for more Cup of Cosmology. So thank you, everyone. Great to have you here. Thanks to you, Dan, for joining.
Thank you for having me on. It was a pleasure. Really fun.